Okay, this is week 9, induction, part D, power line thievery. I want to teach you how to steal power from your power company without having to pay for it. So imagine that you've got some power line coming through your property. Maybe you live out on a farm somewhere and there's this big power line going by and it's got a lot of current flowing through it, and you think, hey, I should be able to somehow make use of that. There's a magnetic field going around this thing, and the power that's flowing through, the current, is switching direction. It's alternating current. So this is going one way and then the other. That means there's a magnetic field going around it one way, and then it's going the other way. It's going back and forth. Hey, we should be able to induce current in a coil that we put near this thing, because the magnetic field lines would be going back and forth through the coil, and that's a changing magnetic field, a changing flux, and so we should get an induced EMF in our coil, and we can use that somehow. Well, let's see if we can do this. The first thing to do is to think, if you've got a power line going by like this, and you're trying to hook up to it, how would you hold your coil? What orientation would you use for the coil? You've got to think about this a little bit, sort of imagine this in 3 dimensions. How would you arrange the coil? See if you can come up with a good answer to that. Which way would you hold? Say you've got a loop of some kind. What orientation would you use to position it to get the strongest effect, to get the best induced EMF from the changing magnetic field? Think about that for a little bit. Can you come up with a direction? The answer is that you want it to be flat. I'm going to draw the loop as if it's a rectangular loop, but it needs to be sort of parallel. One side of it needs to be parallel with a wire, and then the other side extends away so that the magnetic field lines come down and go through this loop. They go right on through and get captured by it in some sense. Another way of drawing this might be to say, well, let's have our power line going by up here with its AC current that's going back and forth that direction, and now we'll set up our loop like so. It's going to be, we want to get something useful, so we're going to have to make a really huge loop to get something. Let's start putting some numbers in here and calculate and see what we might be able to do. So let's imagine that we're going to be 10 meters from the wire. Now, parts of the loop will be closer, some will be further away. We're going to ignore that for these purposes. About 10 meters away, about 30 feet. So this is a high tension wire that's up pretty high, and we're not going to try to get too close to it. We don't want to kill ourselves in the process. So we'll set up a structure down underneath it, some distance away, about 10 meters away. Now, we're going to go for broke. Make this thing huge. You'll see later on that we really do have to make it huge. So let's make this thing 3 meters tall and 25 meters long. It's going to be an enormous structure we'd have to build. And then we're going to run wire around this, and we're going to have 200 turns of wire going around this. I mean, if one loop is good, 200 is that much better, right? So let's see if we can get something out of this thing. So that gives us an area on the loop of 75 square meters. That's the area. What's this? How strong is the magnetic field? As this current goes back and forth down here, we've got a magnetic field going in and then coming out, going back and forth like this. How strong is the magnetic field at exactly 10 meters? We can calculate that pretty easily. The B field, this is just the strength of the B field from a wire with some current flowing in it. Well, we need to talk about the current flowing in the wire first. So, how much current is up here? Let's imagine that the current is 100 amps in amplitude. In other words, it gets up to 100 amps and then it goes down to negative 100 amps, goes back and forth like that. So it's sort of 100 amps times, it's a sine function here. And the frequency of this is, of course, going to be 60 hertz, it always is. And so if you remember how to write that, it's 2 pi ft, so 2 pi times 60 times T would be the full form for the current that's flowing in that wire. This is just our usual 2 pi ft form for a sine function, something like that. So that's our current. So the most that it ever is 100 amps. Let's calculate then what is the B field at the instant when you've got 100 amps flowing up there. Do you remember how to get a B field from a long straight wire? You're some distance away from it. That's a formula we've used many times. Mu 0 I over 2 pi r. So that's, well, now we can put all the numbers in. We've got all of them here. At the moment when the current is 100 amps, then that is, mu 0 is 4 pi times 10 to the minus 7. The current in the wire is 100 amps divided by 2 pi times 10 meters. So we get an answer, we calculate that, of 2 times 10 to the minus 6 Tesla. There's still a sine of 2 pi 60 t. In a sense, that's still in there, right in the B field. The current brings in that piece as well. I just did it with 100 amps, but the sine would also be there. So that's the answer. We get 2 times 10 to the minus 6 Tesla. That's not a very strong field. That's a pretty weak field. In fact, that's down less than the strength of the Earth's magnetic field. So it seems dubious that we're going to get much this way. But let's try and see what happens anyhow. So that's the B field. Next we need to get the flux. How much flux is through here? And then to get our EMF, we need to see how the flux is changing. So what's the flux? The flux is going to be N times B times A. Remember, flux is B times A, and if you've got multiple turns, then you just multiply by N. So we've got 200 turns in our loop. The B field we just calculated is 2 times 10 to the minus 6. And then it's still got this sine function of 2 pi 60 t. And then I'm going to multiply that by the area of the loop, which is 75 square meters. And I will have a flux. Then that comes out to be 0.03. And the units on flux, which could be, this by the way is Tesla. Tesla meters squared is Webers. So 0.03 Webers, still multiplied by this sine of 2 pi 60 t. The flux is changing with time, still according to the same formula. Now we'd like to get the EMF. The EMF is minus d phi dt. So we have to take the derivative of this thing. What's the derivative of that? Well, the only thing that's changing, we take the derivative with respect to time, the only thing that's changing is the sine of 2 pi 60 times t. This 0.03 is just a constant that's out in front. And so that just floats out in front, so we would just have, and sine becomes cosine, don't really care about that, but you're going to have minus from the formula up there, 0.03 times, and then when you're taking the derivative, out comes a factor of everything in front of the t, omega you could call it if you wanted to, so 2 pi 60 times still a sine, not sine, it's going to be cosine now, cosine of 2 pi 60 times t. Well, I'm just going to worry about what's out in front, the EMF, what's the maximum value of the EMF, and when you multiply all that out, you get 11.3 volts. That's the peak value. Okay, so for all of our work, this enormous structure that we set up has a 12-volt signal. That still sounds like, okay, 12 volts, let's buy 12-volt stuff and hook it up and we can use this. Until you do a little bit more calculating and you figure out, yeah, you've got that, but you also have a whole lot of wire that has resistance in it. And so maybe you've got, effectively what you've got is we just found the EMF, but we haven't figured out the internal resistance of our source. So the EMF is 11.3. How much resistance do we have? And I don't really think it's a necessary part of this course, but I have done the calculation. And if you spent a year's labor or something like that to buy an enormous amount of copper wire and used 10 gauge copper wire, that's heavier than you have in any house, and you're still going to put 200 turns on this, so you need, it turns out you need 14,000 meters of this stuff. It's a lot of wire, and this is expensive wire, that you would end up with a resistance of something like 40 ohms. Even though it's beautiful, thick copper wire, you're still going to have 40 ohms of resistance going around this thing. That's with 10 gauge wire. You could go heavier still, spend still more money, and get this down. And at 11.3 volts and 40 ohms, how much power can you deliver? What can you make this do? It turns out, with a little bit of work, you put something out here and try to get the most power delivered to that thing, and the power delivered is about 1 watt. 1 watt for all of your trouble. You've probably spent thousands of dollars on the copper and the wire setting this whole thing up. It also happens to be illegal, but that is sort of beside the point when you do all this work and you end up hardly getting anything worthwhile. So, I'm sorry, this is not the way to steal power from